Alright, so today we'll be learning some basics on ANSYS. So if you go to your VLE, we will have this section, ANSYS Basics. So we're going to do a few examples and then you're going to try on your own lah. So the first one will be this one, which is the first part. So this is the mechanical basics. So under ANSYS, you have to open up something called Workbench. So if you go to your programs, search for Workbench. This one, Workbench. So under Workbench, let's let it launch first. So the first exercise today is for us to do something called basic stress analysis lah. So this is a control box cover. So the control box cover has to withstand an external pressure of 1.1 megapascal. So it's made from aluminum alloy lah. So we have to search this material, aluminum alloy, and verify whether the maximum stress is exceeded yield strength or not yet. So this is the design, and we will be applying boundary conditions at these particular points. There are 4 screw holes, and then we can apply something called a frictionless support at these 4 area and surrounding base, and then applying pressure throughout the whole surface lah. The whole surface will be 17 exterior surfaces. Okay, so let's start. ANSYS. So this is the outline of ANSYS. Under here, you're going to see a lot of analysis that you can do. But the important thing that we're going to be doing today is something called static structural. So you go to static structural and then you drag it out. So take it out. It's going to launch. And under here, there will be something called engineering data. So, and then followed by geometry, and then you've got model and such lah. So let's look at engineering data first. So under engineering data, you can get your material data. So over here we've got structural steel, and this is the only material available for the time being. So in order to add more materials, you have to manually select, or you can grab from the library lah. So if you look at this particular structural steel, there are multiple properties lah it is having. For example, how many properties? 1 until 27, so many. Material table, okay. And then you've got isotropic secant, coefficient of thermal expansion, and even other. So what else? Expand. There is something called strain life parameter. And then you've got SN curve. So you can make your material as complicated as possible or as simple as possible. So if you want to copy certain material data, you have to click this one, engineering data sources. So under engineering data sources, there will be a lot more library lah. So if you want to return back to the previous material data, click again lah. Engineering data sources comes back to structural steel. Click this one, you're going to get a few libraries. Under this library, you're going to see ANSYS Granta, General Materials. Let's click Granta. So under ANSYS Granta, there'll be materials like this one, air, gas, alumina, aluminium rod, 6061, bronze. So these are the material available. You even got concrete. So multiple materials are available. And then there's general material. Under general material, you've got a lot more things. Aluminum alloy. So probably the material that we'll be using is one lah, aluminum alloy. right? If you go back here, aluminum alloy. So once you discovered your material, you can click plus. So once you click plus, and if you go back to your material database over here, you're going to see a new one lah, which is called aluminum alloy. So this is the material that you have. If you want to grab more materials, you can even grab more lah. There are more specific materials. For example, under explicit, this one is for dynamics lah. Here is something called, I think, damage. You can even simulate damage under explicit material. So it's loading. So aluminium, more specific research-based aluminium material, and probably hundreds of material database lah. So under hyper-elastic, you got elastomer, magnetic, you have all these things. Composite, probably you're gonna see carbon fiber is here with a value of 395 GPa. The orthotropic elasticity 395 GPa, whereas steel is about only 200 GPa. Carbon fibers is 395. So you can get a lot of materials. So general is where you find any other basic material lah. So if you hit engineering data sources again, you're going to see back your engineering data lah. So you can even create your own material lah. For example, I can click here. For example, I'm going to key in something called steel MSI. So steel MSI, hit enter. So this is my material lah. So under my material, I have nothing, no property here. So you have to grab the properties from the table from the side. For example, go here, physical properties, click density. I think drag it. You can drag. No, you gotta double click. Double click density, then you gotta key in lah. For example, my steel is 7,800 kilogram per meter cube. So go back here. Under field variables, I have nothing here. Physical properties. These are the things that I can customize my material. Thermal expansion, no. So let's look at elastic modulus. So under here lah, linear elastic. So I'm going to choose isotropic elasticity. So I can double click. And then I got to key in where my yellow color are. So first I have to change my unit first. For example, I change to GPa. So Young's modulus is how much? 200. 200 GPa. Poisson ratio is about 0.3. So there you go. So this is my material lah. Something called steel MSI. So you can make your material data very complicated or simple as you want lah. You can put in lots of things. Life, strength. SN curve is fun. It's for fatigue. So let's stick to, oh, we're going to use this one, right? We're going to use aluminum alloy. So let's go here lah. So engineering data is only for you guys to select your material database lah. So once you complete, you can even click X. So engineering database, there'll be a check mark here. You can go back to engineering database if you double click. So you're gonna come back here and then click X again lah. So next thing we're gonna do, we're gonna import the geometry. So under geometry, we have to download this something called cap fillets. So you have to right click and then save link as. Save it somewhere on a desktop. So if you notice, the format is .stp lah. So it's a step file. So sometimes ANSYS cannot read SolidWorks file, for example. So you need to convert the geometry to something readable lah, for example step or ANSYS. So let's go and import, right click on geometry, import geometry, browse to where you are and look for the file lah. So geometry is also check mark. So this Workbench is something called a dashboard lah. So you can get a lots of material database, and then geometry you can link them. And then we're here lah, under model. Let's double click model. So this is where you do your FEA modeling. So it's going to launch, taking a while. So cap fillets. Okay, let's go here. So there'll be two windows lah. One window is for the dashboard for your Workbench. The next window will be your ANSYS mechanical lah. So over here is going to read the data from the geometry, and then you can start doing your modeling. So this is the geometry. You can rotate using your center mouse button, zoom in and out, and then you can zoom using your right click. You can even fit view back. Click this one, fit view, zoom to fit, and then you can pan your view if you click Control and center mouse button. Control and center mouse button is going to pan your view lah. So pan is very important. So over here, if you go and browse under geometry imports, there will be this one lah, geometry import A3, and then there'll be under geometry, there'll be this one lah, cap fillets free parts. So there is no more right click. Yeah, you can right click also lah. Currently this geometry cap fillets, the material is default selected as this one lah, structural steel. So if you want to change to other material, you can lah. So there'll be this is the current material that we have created on our own. We are going to assign this one aluminum alloy, so has been changed lah to aluminum alloy. And then so that is how you set the material geometry. So under materials here, there'll be these three materials available under your database. So once you've done that, you can go to mesh, right click, you can click update. It will generate the proper mesh for the geometry model. Currently at 5%. And then this is the geometry that you're left with, the default geometry. So you can check things like, for example, quality, check mesh quality, yes, error. Inflation, advance, and also can get the statistics. The statistic will tell you how many nodes, how many elements. So this is the default way you can mesh lah. So if you want to go advanced, you can go back in the mesh, and then you can insert lah if you want to control things. For example, I want to control sizing. Let's say I want to make certain area the mesh become smaller. For example, this one. I can hit control lah. If you want a multiple select, you have to press control on your keyboard. So let's say for area, I want to control the mesh density. Click here, click apply. So there'll be 4 faces that you can control lah. Face sizing. So currently the default is 4.8. Let's say currently 4.8, right? I can change this for example 3. So these 4 surfaces will be controlled to 3 mm. And then I have to remesh, generate mesh. And then the sizing will be changed a bit now at that particular area. Yeah, it's changed a bit. It's changed a bit from the previous one. So we can explore on how do we control mesh here lah. Under mesh. So not only face sizing, you can control lots of things lah. Even topology, mesh, face mesh, refinement. Probably a good thing is refinement lah. How many you want to make the volume fine. So for default one, you can do this one, or you can just eliminate lah. So if you want to delete this one, just go to delete on the face sizing. And then definitely you got to generate again lah, generate the mesh again. So goes back to original lah. Currently the material is now aluminum alloy, correct already. And then if you see here, you can see all the checkbox. So all the checkbox are okay. So next thing we can do is that we can create some boundary conditions. So you have to go to under here, static structural A5, and then you gotta insert certain things lah. For example, you can insert things like frictionless support. So frictionless support supports the face, so you can only move on the surface direction lah. So this you have to read here. Frictionless support, insert a frictionless support to prevent one or more flat or curved faces from moving or deforming in the normal direction. So it's not going to move in the normal direction to that particular surface. So you can choose this one, or you can choose fixed support also can lah. Fixed support is controlling X, Y, Z lah. So let's say I want to choose fixed support. I want to control at this particular face. So I have to click control and select all my faces. Face, another one, I can zoom lah. And then control. So make sure you choose all 4 faces. And maybe I can click apply. So all 4 faces has been selected. Can fit the view. So under fixed support, if you click on fixed support, it will highlight lah, fixed support on all 4 faces. Yeah, again, you can also use fixed support. You can use frictionless support also can lah, as per the thing that is asking you to do, this one. Frictionless support also can. This one is acting on the base lah. Okay, next thing we want to do is we want to insert some loading. So under load, there will be things like pressure, force. So these are all the things that you can apply to your model lah. So let's choose pressure. Geometry is here. So under geometry, this is something called smart select. So it will select smartly lah. If you want to control, I want to select face only, I can choose this one lah, face only. Or smart select is okay. So let's select define by normal to, or you can choose normal to lah. Geometry, yeah, this one is surface pressure, normal to, correct lah. Selection, so select all the surfaces. How do you select all the surfaces? You have to click control, that's the problem lah. Otherwise it will not multiple select. So you have to click control all the time on your keyboard. And then this small surface also have to select, meaning I gotta fit the view and then zoom it a bit and then control, then click here back, smart select. I have to select all these surfaces. So control, and then some more. How many surfaces already? If you have selected most surfaces, you can click apply already. So I missed out one face lah, 16. One more surface, I can click again, hit control, gotta zoom control, so then click apply, we select 17 faces So all surfaces has been selected. Make sure you apply the value, which is 1.1 megapascal. So the value will be ramped from 0 to 1. Pressure is normal to, which is correct. And then there you go. So you have your boundary conditions, and then you have your loading. So let's take a look back at this one, analysis setting. So there'll be number of step, one step, and time is 1 second. So from 0 to 1 lah. However, this time is not actually time lah. It is actually pseudo time lah, imaginary time. So from 0, it's not actually 1 second. It's just a pseudo one. So pressure is okay. So everything is okay. So under ANSYS, there is no results that is pre-selected. You have to key in, you have to select what result you want lah. So under solution, you insert, for example, you want to know total deformation. You want to know what is the strain. And then you want to know what is the stress. So you have to select what you want to know. And then you can right click here and then you can solve. Okay, so it is running using 620 megabytes of memory. And then we're done lah. So once everything here is okay, so it's done. So this is the solution information. If you have any problem, you can see here lah, any errors or anything. And then this is the total deformation. Let's fit the view and then look at it lah. Fit the view. So currently total deformation, this is already in what unit, millimeter. So deformation is quite small lah, around 0.2 millimeter only. However, this is exaggeration lah. How do I change this exaggeration? Total deformation. Actually, you can change lah how much it will exaggerate the views. Let's look at other things first. For example, stress. Stress quite high, but where is the high? You don't know. So one of the easiest way to check your stress, you can look at your yield stress lah. So aluminum alloy, what is the yield stress? You can click on aluminum alloy, it will tell you this is the value that it is using lah. Tensile yield strength 280 megapascal only lah. So tensile yield strength 280 megapascal. So let's take a look back. Under equivalent stress, you can click the don't click the top I don't think you should click the top lah. The top, let it be. Can you click the top and then change 280? Cannot, right? Cannot. You can only change the second one, I think. 280. Is it megapascal? Yeah, it's already, the unit is in megapascal. Where is the high stress coming from? Is it coming from the location of your constraints? Is my pressure correct? 1.1 megapascal. Correct lah. My equivalent stress currently internally. So you can see internally lah. This red color at the corners here, this is areas of high stress where you have the corners there. Okay, so if it's not very clear, I guess you can do certain things under display. No, result. This is where you should look at. Don't look at under home, go to result. Currently, if you see here, 23 auto scale. So the deformation has been exaggerated by 23 times. If you go here, through scale, you can barely see any deformation lah. So that's why it will automatically auto scale to certain deformation so that the engineer can see. If you change to more, for example, 46, it's going to be much greater. However, this is not true one. This is 46 times. Maybe 23 is good enough. So what else can we do now? How do we determine the location of the highest maximum stress? You can click here, maximum. It will jot down maximum, minimum, close to 0. Or you can click on probe to determine stresses on certain area certain areas of interest. The contour you can change to smooth, maybe not so good. Contour bands are good. Edges, we want to show the elements or wireframe or show undeformed model. So many things you can do lah. Show undeformed model, no wireframe, show element. Show elements lah. Normally you have to show the elements. What is the mesh density that you're using? And then what else can we do here? You can do section plane. New section plane. Just use mouse. It will cut for you lah. For example, over here, want to look at the stress over here. So this is the section plane that I can cut off. I can turn it back on or off lah, toggle it. So don't worry about here. You can still go back to here lah under details. What else? We need to determine whether this thing is having problem or not. So if you look at 280, you're not gonna see much. You can see some more if you change to this one to lower. For example, you go to 100, and everything is red lah. 100. Now you can start to see locations of high stress lah. So you have to play around with the values of maximum, not maximum, the second one. Can this be dragged? So this is a better representation of the problem lah. Changing this scale. If you go automatic, or you can add or minus the scale. How do I change this back to automatic? Vertical, horizontal, all scientific notation, quite good. So if you change the second one to 200, can you see a good representation? No, not a good representation. 50, not a good representation. 100 is a good representation lah. You can clearly see which area you need to improve if it's required lah. Okay, so this is under stress. Look at deformation. And then you can look at strain. Okay, so everybody can do this and screenshot your answer lah. So if you click X here, that is still okay. Everything is still under here, under solution or under results. You can double click results. It will still go back to your original thing that you do. Or is it? So it's going to take some time to load lah. Or click solution. It's loading. So it loads it up again. So all the results are still here. So you don't have to worry lah. So you can save the project lah. This one, if you turn it off, you can save the project lah. Save as. And there'll be this one, this project file, WBPJ. WB is Workbench, PJ project. So this is how you do a basic static structural analysis. So if I want to change to a different geometry, I can right click here and then replace. Replace the geometry or whatever I want. I can even delete the geometry. Oh, this is engineering database. Go to geometry, replace geometry if I want to do it. Okay, so do that one first, and we'll go on move to do the second one. Let's look at this one. What is it? This is on impeller type pump. Analyze the assembly of 100 Newton load on the belt to confirm whether the deflection of the impeller is not more than 0.075. So this is the problem, 100 Newton load. It's telling you the examples on how to do. Under general material, and then how to apply the load. It is currently applying something called a bearing load to the surface. And then change certain behavior to no separation. So once you do this analysis, you can get some static results lah. So it's not very hard lah, this one. So the only thing that we need to change under here would be this one lah. Contact behavior to no separation. Okay, never mind. We'll skip this one first. Maybe we'll do this one later. Do something else. Let's do something called a tensile test. Let's download this one. So this is another analysis. Something called tensile test of a specimen. So we have a specimen here, and then the specimen diameter is 14 millimeter. And you would like to test it under tensile testing. So if you look at the problem here, it is given your material properties in this format. So you've got all this data in this format. So let's say you don't know what kind of material this is. Maybe this is steel, but you don't know what kind of steel. So this is the material database which you use to test in your materials lab. So you can even model this particular material behavior. If you look at your testing under load, there'll be your sample will behave like this lah. Necking and then fracture. So this is the behavior, or normally it will be under elastic strain, and then there'll be plastic strain, and originally there will be elastic deformation, a straight line to determine your Young's modulus, and then they'll be changed to this kind of behavior lah. Once it does necking, then it will fracture. So if you look at it under material testing, there will be two kinds of stress strain lah. Number one will be the engineering one. So engineering one, the behavior is like this lah. This is engineering. However, if you go to something called a true stress strain will consider the decrement of the area at the necking. So once the material become necking, the area becomes smaller. So stress is different already. So when you do FEA, you will always use true stress, true strain lah, to put in your value. So this is an example of a representation lah, of true stress strain. Just using two data sets. Okay, so let's model this. You have to download this one lah, specimen tensile test. So you can right click and save link as, save it somewhere. So this is a SolidWorks part file lah. If you open it up, you're going to see a SolidWorks part format. And this is how it looks like. So this is how it looks like. What is the diameter? Go to evaluate, measure. Diameter here is 14 millimeter. Measure from here to here. Distance, point to point. Measure here to here, 126 millimeter. So this is your original previous work, right? You can keep it. You can put one more analysis here. So you can have two different study in one dashboard lah. Or if you want to delete the previous one, you can also do so lah. Delete the previous one. Only one analysis you have now. So this is something called a toolbox analysis system. So under analysis system, you can do this lah. Everything is connected. Or you can do individually. You also can component. Under component, you can under custom, under component lah. For example, geometry, you want something else. And then where is the engineering database? Engineering data, you want something else. And then you want to put your static structural here. You can even do that lah. Can you rearrange this one? Cannot, it's automatically. For example, this geometry, I import, browse to my specimen tensile test. Currently it's detected lah. If it's not detected, you have to go to your SolidWorks and then file, save as, to maybe step file. This one. Either one is okay lah, step file. If you cannot detect, if it is detectable, then it's okay lah. Change to step file and then you can import. So this geometry, you can link this geometry here, share with A2, like that. And then engineering database, you can also share here. So meaning if you have more than one analysis, for example, next analysis you want to do explicit dynamics. This is another analysis. You can even share your geometry here. So you can do lots of sharing with lots of analysis lah. Engineering data also I want to share here. I can do lots of sharing lah. So if you don't want this, you can stick to the system lah. You don't want this, delete. You don't want this, delete. Explicit dynamic, delete. So this one is a whole system lah, standalone. So let's go back again. Engineering data, double click. So there'll be this one lah, structural steel. So the problem now, I have a new material lah. So this new material, you have to create your own lah. So I have to go here, click add new material, specimen steel. Maybe the name is like that lah. So this is a new material. I gotta add my physical properties lah. So under specimen steel, I'm adding things like density. It's not required lah to add, but it's good to have lah. 7,800 kilogram per meter cube. So specimen steel, I have density. I need them for any dynamics analysis anyway. And then maybe next thing I can do is put some linear elastic lah, isotropic elasticity. So double click. So this will be the Young's modulus. So how do you calculate Young's modulus? You have to go to your material database lah. So over here, you can get Young's modulus lah. Where is it, the Young's modulus? So go to a pen here. So this is the Young's modulus lah, stress over strain. So E will be 450 megapascal divided by 0.00225. So what do you get? What is the Young's modulus in megapascal? Or I think in gigapascal. In gigapascal. So 450 divided by 0.00225. 450 exponent 6 divided by 0.00225. So you're gonna get 200. 200 gigapascal lah. So this is the value. So let's key in the value. SolidWorks you can turn off already lah. So this one will be 200. So currently it's 200 Pascal. So if you change this one to gigapascal, this one already changed wrongly lah. So always put the unit first lah, then put here. This one is 200 now. 200 gigapascal. Poisson ratio 0.3 lah. Just choose a default value of Poisson ratio. Okay, so this is done. However, we need to add one more lah. Choose my specimen steel. I need to add something called a plasticity, because this graph has plasticity region, so I can add something called a bilinear isotropic hardening lah. I can double click this one. So this is my bilinear isotropic hardening. I can key in something called a yield strength. So my yield strength is 450 lah, 450 megapascal. So change unit first, megapascal, and then 450. So that is the value, and then tangent modulus. So tangent modulus, I need to calculate lah from the slope here, from the graph. So if you look at here, let's calculate the slope. How much is the slope? So this slope lah, this slope over here. So 500, 450, 0.03, 0.0025. So this is the tangent modulus lah. So 500 times to 10 to the power of 6 lah. Careful. I'm gonna erase some things here. (500) E6 minus 450 E6 divided by 0.03 minus 0.0025. So this is the hardening slope. So let's find out. 0.03 minus 0.00225. So this is 0.02775. This one over here, you're gonna get 50 lah. 50 is 6. So what is the value? So it's actually 1.8 E9. 1.81 E9. So that is the value that we should put lah. 1.802 actually. 1.802. So let's plug in here. The unit will be Pascal kah? Yeah, Pascal. 1.802 E9. Enter. So that is the value lah. So this is your own material database using this testing database. So now let's do it again lah. Let's click on engineering data sources. Yeah, you don't need anything from here. Turn it off. You can click X lah. So engineering data is correct already. Geometry, have you imported? Right click, replace geometry. I think it's already there lah. Specimen tensile test. Just click model lah. Go and click model. Is it the correct geometry? Okay, so the specimen is correct lah. Let's look at our material. Is the material okay? Yeah, I've got it here. Specimen steel. This is the bilinear isotropic hardening. The graph is also here already. This is the graph. 450 zero plastic strain. This one, how can I make it smaller? Cannot lah. So under geometry, and then under geometry, click plus here, and then under part 1, we need to assign the material lah. If you click part 1, oh, it's nothing here because this section plane is on. Go here under details. So the material assignment is always default as structural steel. You have to individually change this one. Change to specimen steel. Then it's okay lah. So your part 1 now is already specimen steel. So your geometry okay, specimen okay, and then click on mesh. Generate mesh. So it will generate this kind of hexagonal element lah. Currently the mesh, the sizing is just default. Sizing resolution 2. Can I increase? And then update. Will it make it smaller? Oh, change the topology altogether already to tetrahedral. Resolution minus back. And then generate again. Yeah, change back to tetrahedral. So let's stick with it first lah. So the thing that we need to do here, we are conducting a universal testing analysis. So you need to put some boundary condition lah. Insert fixed support. So you want to support at the top here. The surfaces at the top, click apply. So the surfaces at the top has been hold. And then next thing you want to do is you don't want to apply force because when you're doing tensile testing, the force change as the specimen move. So what you want to do is you want to apply something called a displacement. So the gripper is down here, right? So you apply displacement at this surface. You want it to go down. What axis would be? Which would be axis X lah. So how many millimeter? Maybe 15 millimeter ramped. Is it going up or going down? I think this is going. Let's check it first. Geometry, no selection. Okay, click here and then click apply. The arrow is going up lah. So you want to change the direction, put negative . So now the arrow will be going down. So you got fixed support, you got displacement. That's it lah, pretty much. I gotta put your solution. What do you want to know? Insert total deformation. You want to know stress. and you want to know your strain. This is the things that you want to know lah, and then you can solve. Right click on solution, solve. So it will ramp the model from 0 mm to 1 mm, 3 mm, 10 millimeter, and then until 15 millimeter lah, slowly ramping it. It's going to take some time lah to solve. Currently, the progress is at 3%. Oh, 1%. Solving mathematical model now. I'm going to pause. Okay, so let's take a look at the results. So total deformation is like this. You can play it, see the deformation. 15 millimeter max lah. And then look at stress. And then look at strain. So if you want to look at from the top, just click X, I think. Click X, it will become like that. And then if you want to section the view, how do we do it? Go under result, section plane. So you want to see this one. So now you can watch what happens. Currently I have edges. I can yeah, edge show element is good. Depends on whether you want to show your elements or not. No wireframe. And this is everything. So the good thing is you can really verify the stress data. For example, if you look under average, there are many things is plotted here. So this is elastic strain. Let's look at stress. This is the behavior of the material data. Maximum. So don't look at minimum. Minimum is too small. Don't look at average. Let's look at maximum. So the maximum is behaving as what our material data. So our material data as what we key in at 0.0 t, it's going to be 0.500. Is it correct? 0.03 somewhere here. 0.03 somewhere here. How do I make this value smaller? 500 is supposed to plot to 0.03 lah. Currently it's plot everywhere. So it's behaving as per our material database. Just make sure your part is choosing the correct specimen still. it will behave properly if you select the proper material database. This is the material behavior. There is a linear region, and then there'll be the plastic strain region lah, as the analysis is done. So at least you have to do these two problems first and then screenshot your results, and then we can move on to more advanced and more complicated things lah. Okay, so that's all. Thank you.